how ZigBee is used to some extent, but we're not going into any of the details. All right, so the idea is that this is used in a personal area network with short distances, and so the short range wireless communication is offered by ZigBee at kind of a lightweight manner. So the idea is that you have a topology. So topology is meaning that you have a whole bunch of nodes, and they may also forward packets for one another. You could have that. So you can have all kinds of topologies, like a single hop star, which means something like you have sort of a central node. You have other nodes that communicate through that node, and so you can imagine you can always communicate from one side through the central node to the other node. But you can have all kinds of difficult networks, and obviously if you look at the internet, by the way, as a whole on the earth, then the topology looks kind of, there have been studies about what it looks like. It's some kind of, you can describe it by a graph where nodes are connected to one another, and you see kind of interesting features of it. It's not, it's a certain type of graph. Anyway, ZigBee, it's reliable and robust, low power, blah blah, scalable. It supports networks of thousands of nodes, so that's kind of interesting. And here it also states, right, providing a networking for the smart home or the smart city. Actually, the idea of the smart city is has gotten a lot of traction, and I would say that is absolutely a hype for the modern engineer. So the smart city, you can imagine, has smart end nodes in the sense that there's some compute power there, so you could do some computation, you can do some data analytics, but you can definitely do better on resource scheduling and stuff like that. So think about the sewer system, the water system, the traffic lights, the of course our mobile phone connections, power supply, all these infrastructures. They can all be connected in a smart way to some extent, and you could even provide security, if you will. Like I remember when I was a research scientist at MIT, at some point I think the city, representatives of Dubai came to MIT, and the idea was to create a smart city completely from scratch, did not exist before, that would be the city where there would be a stock market for oil, which would be kind of different. And then you would want to provide all this infrastructure, you would bring in smartness, and we were there for the security, because that's my field, security. And in this case they also wanted to have really like Big Brother type of monitoring with cameras, which now I would say is widely spread in the United States, and certainly Britain and other places. You have, and in China too, by the way, so you have tens of thousands of cameras monitoring what's going on. But so there's already that monitoring mechanism, but the smart city is really cool. So I think right now MIT is offering a definitely a minor, if not a major, in smart city engineering, which is pretty interesting. They're kind of one step ahead of the rest, I would say. But the point is, though, that for your own futures as engineers, you can imagine that would be pretty cool. But to think about, now, a smart city obviously uses everything that we're studying here, like it's based on microcontroller technology, right? Okay, so it's scalable, secure, it offers some encryption. You may have heard of the advanced encryption standard. And it is global in a sense that it's built on this frequency, and it's available for unlicensed use anywhere around the world. So some technical notes that we may not need to go over, but so you can look at the specifications. What kind of methods does ZigBee use to achieve low power consumption? There's some details over here that I actually forgot to look over, but it's definitely efficient, and it definitely goes into sleep mode whenever it's not being used. So, all right, so how do you compensate for interference in this global band, because everybody can use it? So you need to have some form of a digital signal processing protocol, if you will, that allows the Zigbee nodes to really recognize one another. So they use 16 separate channels in this band, and several of these do not overlap with the US or European version of Wi-Fi, so it's already good, etc., etc. So they try to be cognizant of what's happening elsewhere. But the point is that you would create a specific type of signal processing protocol that reduces this probability of interfering with other users. So you sort of hop around and you try to listen. So reliability, again, you use direct sequence spread Sprectrum. Maybe you have done a digital signal processing course, and all of that is implemented. So as a user or designer, you will not obviously see all of this. You'll just buy the product, and then you have those units just like your CAN controller. You just need to program it. So a ton of nodes can be supported. So if you look at the Zigbee layer protocol model, you clearly have the application running on top of an application layer, a network layer. Then you have the medium access control layer, and then you have the physical layer. So these are part of standards. This is a standard that defines all of this. So on top of this is, say, the Zigbee standard, in a sense, on top of that. And then the application is using this. And that's sort of where you will be. Besides that, you also want to make sure that when you buy the product, it works properly. So you need to set the bits properly and so forth. So, all right, so here's some explanation. So the physical layer is really all about the basic communication capabilities on a physical side. So it's all about the channel selection, the digital signal processing that we're talking about, and all of this is part of that. Next, we have this access control layer. So for example, the important parts are here in black. So we have encryption. We also check for integrity and access control. So integrity meaning, so encryption meaning that someone who looks at the packet encrypted, well, it doesn't have the secret key how to decrypt it, so it doesn't make any sense. It looks like a sequence of random bits. But once you decrypt it, you get some data, but how do you know it was not, into some extent, is that the most recent packet, for example? Is it fresh and stuff like that? So you want to check that integrity of the packet, so it's not a replay of something older, and also you want to make sure that there's access control. So are you allowed, or is this packet, is this packet coming from someone who's allowed to do, to have access and so on. Alrighty, so there's a bunch of details that we're not going over. You can look at this. The slides are in your directory. All kinds of modulation types, which is also quite interesting. A long time ago, I actually worked in digital signal processing for industry, and I remember working on signal constellations, for example, and error correcting codes. I worked in Blu-ray disc actually at the time. I'm the lead inventor of the error correcting codes used in Blu-ray disc. That were the first 5 years of my, after my PhD, of my scientific sort of research career, but after that I moved into security. And then, if you have a chance to ever be part of developing like a product that gets out into the market, it's just wonderful. If you're lucky. You gotta be lucky. It's really what it is. Anyway, so it talks about all kinds of things: access control, encryption, integrity, and freshness. And there's some more details we're not going over to. Lots of details, all kinds of encryption possibilities. So this whole security suite, you can define, or you can explain what you would like to use. So it's a combination of encryption and message authentication often. Um, an application profile. So at the application layer, we talk about application profile. So profiles are the key to communicating between devices on the network, and effectively, you need to sort of upload. You need to at an initialization. At initialization, you would need to sort of register your profile with, say, the master in the network. So we'll get to that in a moment. What's all this? So yeah, so that is that. All right. So this is, for example, so this is an example. So if an application layer, so you need to sort of, so if you look at the OC model, it's a way to explain, I don't know whether you've heard of it, but it's explain of looking at all the different layers that are on top of one another when you do communication. So you transmit over the physical layer, but then there's a first protocol, which is the data link layer, then you got the network layer, transport layer, session layer, and all of these is what is called the OSI model. But these layers are being compressed together into the previous slide. So these two are part of the physical layer and the data link layer, and all those four are part of what we call here the ZigBee network and application layer, and then we have the application layer on top. Alright, so what about the star network topology? So we have different nodes. So we have RFDs and FFDs. They are different. So full function device and reduced function devices, whatever that means. We'll come to that later, I think. And then we have a coordinator in the middle. So you can communicate. So with the star network, everything is connected. And so let's have a look here. So the FFD is a node with the resources to perform more complex tasks, such as becoming a coordinator, or a router, or an end device. And over here is a node with limited possibilities, and this is just an end device. It cannot become a router or coordinator. So these star networks could be connected to one another as well, right? So, okay, so a lot of terminologies here. So if you're really interested in this, I think this slide deck gives you a lot of background, and you know, we don't have to go over all of this. But what is interesting is that you know, you have different types of network topologies. For example, this one is a mesh network, and the idea is then that you can have several of those together, and I think, oops, and you could communicate from one to the other. Oh, this is, by the way, sorry, this is an example of reliability and robustness. So suppose one node fails, and originally we were transmitting through this, through these two links. Well, there's also this other path that we could use, right? So if this node drops out, we still have another path. So if you have a mesh network, it offers more reliability because you can still connect, even if some of those drop out. There are the cluster tree network topologies. It all depends on you, how you set up your topology and your network. And as you can see, there's more connections. You can connect from here all the way to there, and so on. So how do you join a ZigBee network? Well, we have the coordinator in the center, and we trust it. That's one thing. So what does it provide? It provides the cryptographic key establishment, the key transport, the frame protection, device management, and all that. And so you can select a stand or a high security mode. So the cryptographic keys, just to talk a little bit more about that, you have like different types of keys. A master key, which is very important. So if you lose that one or it's compromised, then clearly anyone with access to that could do everything that the master key can use for. So it's used for key establishment between points. That's pretty important. So then you have link keys, so shared exclusively between two network peers for communication together, and other keys. So there's all kinds of stuff that manages that. So it's quite complex in a way to get it all done in the proper way. So I think that's maybe the takeaway that you can get. All right, so let's skip this. So the key establishment process. You do that in a certain protocol, right? So you first have a device that shares the trusted center link key with the trust center, and then you start to get a transport key, and so forth, and you go through all these steps. That is a bit out of the scope of this lecture maybe, but it's in the slides, and you can set this up. But it's all done for you, right? So so what you do is the node contains an initial trusted TC link key to start off with, and then the node joins the network using a message authentication code type of association. So you start to recognize one another. Then you get a network key and so forth. Is secured with the key A, so this can, if an attacker sees this, it doesn't really leak anything to it. And then you get a new link key, blah blah, and that's sort of the protocol. You get the new link key, a key B, and then on receipt of this link key, the node issues a command to the TC, secure with key B, and that's how you go forward. So this is sort of conclusion, so the introduction of the basic concept of ZigBee, and you, after this short very global talk of mine here, you just get a little bit better feeling of what ZigBee is, and you got to remember that it is widely spread. It's used pretty much everywhere as a wireless communication protocol between tons of nodes. Think of the smart city connection, which is pretty cool, and you can use this slide deck later on if you use this stuff to just have a better feeling for what is going on in ZigBee. But again, all these layers will be abstracted out for you, just like how we work with the CAN controller. Yeah, the physical medium layer, you don't see that. You are at a more higher abstracted level, busy with programming your own application on top of, say, ZigBee or something else. So you just need to be able to install this stuff in a proper way. All right. So we happen to have a project in my lab where we have built a sensor. We have 50 sensors that are all using the ZigBee communication to communicate to a centralized, say, master. And why do we do this? Well, we're doing experiments on how we can collect data from the sensors and then use some smart cryptographic techniques to do computation, what we call under encryption. So you take the encrypted data and you can manipulate it, and magically you get an encryption of, say, the aggregate function of what all this data, of the aggregate of all this data, or other kinds of things. Anyway, so we wanted to create a test bed, and I just wanted to show you that we have something like this in our laboratory. So we have a bunch of these sensors, and they're all hooked up with the master board, and it's kind of fun that you can make it work. But it took some time by my students, and I don't even know the details, to get it all to work. As you realize when you work with your CAN controller, right? It's the same thing. You have a question? I thought you wanted to say something, no? All right. Cool, so some references. So let's talk about I think this one or this one. No. Yeah, so you will be working with Bluetooth though. So, but again, this is a higher level overview, and we'll come back to Bluetooth in much more detail much later on, like before the spring break. And well, Bluetooth is a wireless technology used to transfer data between different electronic devices. The distance is very small in comparison to other kinds of wireless communication. It's wireless, so that's pretty good. It comprises, processor, radio, and antenna, and it works with. Wait a minute, what does this say? Converts the data into signals, and it works the best, I think, within about 30 feet distance. Right. So it's very short range communication. So what is Bluetooth doing? Well, it uses a frequency hopping spread spectrum technique, and it is a modulation technique. So what's happening is that frequencies are switched repeatedly during the radio transmission, and that helps to reduce unlawful access and so forth, eliminates cross paths or generally noise, I would say. You could have the communication is 1 megabits per second. There's a certain ranges that it works really well on, and it works in the personal area network. Here you see a frequency hop function. Effectively, you first try this channel, for example, or not try, you transmit something here, a packet, then you do the next one, and then another one, and so forth. This happens to be a multi-3-slot packet, then you hop back here, and so forth. So you go back and forth over all these frequencies, and that's how Bluetooth signals packets. So what are the applications? So as we see it's a cable replacement, but it's used, in all kinds of devices. I think your mobile phone probably has Wi-Fi. Actually, may not have Bluetooth, but it can, for example, be used in a cordless headset, conference table, or the remote control that your guys are going to build. So was originally studied by the company called Ericsson. Maybe you've heard of it. A famous big company at the time. Was in. I actually did a 3-month sort of student exchange with Lund University. I studied in the Netherlands, and so I went over there. And there Ericsson had its main headquarters, so you can imagine there was a lot of input. Just like with UTC here, with UConn, you had Ericsson over there with Lund University. So pretty interesting. So the Bluetooth specifications were created, it's so you can use it. So that's great. All kinds of specs. In the end, we have a stand. We have all kinds of. So this is the whole history that we see. So it's a long history. It's an open spec, low cost, power efficient, and so forth, easy to use. You will see that it's easy to use. It's going to be your easiest laboratory in this whole set. So again, you have the same type of layers that we saw before, and everybody always talks about all of these layers, but this is pretty standard. So the Bluetooth stack includes protocols for the radio layer, all the way up to the device discovery and service discovery and so forth. Oh, so we have the usual stuff over here. So here we have the layers. Physically transmits, receives data wirelessly. You have the baseband link controller, and we control the links to the other devices, end-to-end communication, multiplexes, demultiplexes data from the higher layers. We have a serial interface, allows service discovery among Bluetooth devices. So all kinds of layers. Now the radio band, as we said, has a whole bunch of, so let's see,